One of my favorite little lessons, the momentum and impulse lesson. I've got a couple demonstrations for you. One with the giant tubes, and if I get a chance at the end, I'll show you what those tubes are actually made for. They're not made for what I use them for. If you drop a magnet in, it's kind of cool. So hopefully there'll be time to show you that at the end. So today you've got all the notes. I'm not even going to make you write anything out.
Oh, you never make a trailer something.
You might have to write out the sample questions. Okay, so we will derive the impulse momentum equation from Newton's second law. It's like super easy. We will relate the impulse momentum equation in real life situations like golfing, and we will solve problems using the impulse momentum equation. I will start with one of my favorite demonstrations. This is known as the Astro Blaster. That was a lot of fun. What does that have to do with golf? Well, let me explain. Here we go. So, the nature of momentum. Consider the following examples. Car and train are traveling at the same speed. It would require more force to stop the train than the car. How come? Because the train is considerably more massive than the car, right? I was going to expand one there, but they're the same picture. So, yeah. The train is much, much bigger than the car, so it has more momentum. A bullet fired from a gun penetrates a wood block more than a bullet of identical mass thrown by hand. How come? Because it's traveling faster. So the idea of momentum, right? These two cases are results of momentum. Momentum is the product of the mass of a moving body and its velocity. You wrote that down yesterday. P equals mv, and we went through that big, long, detailed explanation of why we use the letter P, and we don't really know why. Here's the derivation part. You might remember from the good old days, A is equal to delta V over delta T. Newton's second law states that F equals ma, so I'm going to take this value for A, and I'm going to plug it in there, and I'm going to get F is equal to m times delta V over delta T. Good so far? Okay. I'm going to rearrange that. I'm going to get the delta T out of there. I'm going to multiply both sides by delta T, and we rewrite it as F delta T is equal to m delta V. And this is known as the impulse momentum equation. I like to call it FAT equals math. F delta T looks like an A, F A T, FAT equals math. Impulse on the left, momentum on the right. Okay? The product of a force and the time interval during which it acts is called the impulse. And we use the letter J, not joules, the letter J, the symbol J, for impulse. J is impulse. F delta T. Can also be referred to as the change in momentum. So that's why it's called the impulse momentum equation, because the impulse creates a change in the momentum, which is exactly what happened in the gym in both those situations. I created an impulse, and depending upon the mass, I got a certain change in velocity. When I changed the amount of time that the force was in contact, it changed the momentum. I don't know, let me explain that. Or does it go straight? No, here it is. So, since the change in momentum depends upon the force and the time that the force acts, this has some use in sports, things like following through and the blow dart. So let's talk about the blow dart. When I blew the marker just with my mouth, where did I put all that stuff in?
The marker was right there.
Is it?
Everyone left and then the marker was still there.
Oh, thanks, man. Appreciate that. Where's the copper tube? Oh, did you? Okay. So when I just blew it out of my mouth, how long was the force of air in contact with the blow dart? Not very long at all, right? I put it in my mouth and I went. The force isn't on it for very long. When I put it inside the copper tube and I blow, the force of my breath, the air, pushes through the tube and it's in contact with it for a longer period of time because there's nowhere else to go, right? Like the barrel of the gun. There's nowhere else to go. Did it go farther? Did it all sit right when I blew it out of the copper tube? It went a lot farther, didn't it? And when I used the aluminum tube, the force of air was even longer, a greater amount of time. Let's look. I want you to write down beside this picture here, right? So if I go F delta small t, I get a certain change in velocity. And if I go F delta T a longer time, does the mass of the dart change? No. So what has to change to keep it equal on both sides? Change in velocity, which means it goes faster and farther. And if I use the big giant height, and I have a giant amount of time, does the mass change? No. What has to change to keep both sides equal? Delta V. It goes farther. What does it have to do with golf? Or baseball? Not the more force. Because what? More time. When you follow through, okay, I'm just going to get a tube here and act as sort of like a golf club or a baseball bat. Right? When you follow through, ball comes in contact with the bat, and then you follow through and you actually apply the force over a longer period of time, which makes it go farther. When you bunt, the ball hits it, how long is the ball in contact with the bat? Hardly at all. In fact, to reduce how far it goes, what do you actually do? Pull it back. So you, in fact, slow the ball down before it bounces off. That's the idea of a bunt, right? Baseball, same idea. You want to follow through. Tennis, same thing. Just about any sport where you're hitting something with something else, racquetball, you name it, you want to follow through. That's the reason why. It's not because it looks cool. Okay? Some people think, well, yeah, once you're following, there's the, did I show you guys that the video with the slinky, the Australian dude? No, he talks about golfers finishing with a flourish, meanwhile the ball's already halfway to the hole. Well, that's true, but because you think to follow through, you actually keep in contact. I'm actually disappointed with the physics process and all that. That's pretty basic stuff. I might have a chance today. Maybe. Okay, so here's some sample questions to go with that. Okay? The reverse is also true, by the way, when you're talking about collisions. How come the front of a car is supposed to crumple? And what it does is it increases the amount of time that it takes to slow the car down, which means it's less force. So it doesn't hurt as much. Okay, so sample questions are pretty straightforward. What force will give a 1 kilogram mass, a velocity of 4 meters per second in 3 seconds? That is a fat equals MAV question. We're solving for force. It's 3 seconds, so F times 3. The mass is 1. And the velocity, now it's going from 0 to 4, so the change in velocity is 4. F is equal to 4 over 3, 1.33, I guess, newtons. These are pretty easy.
So why do you put fat equals MAV when you're doing the delta thing? I don't understand that.
Say that again?
You call it fat equals MAV, but it's not an A for assumption.
Oh no, it's just the A, it's just a way of expressing that. It's really F delta T is equal to M delta V. It's just a,
Being cool.
yeah, just trying to be cool.
Following through.
Yeah. You don't like it? Then don't call it fat equals MAV. I won't allow it. It's my own little invention.
Oh, okay.
If you say fat equals MAV, I'm not helping you.
All right.
What about a 10 Newton force acting on a 2 kilogram mass for 5 seconds? Find the impulse, find the delta P, and find the final velocity. Impulse is just the F delta T part, which is labeled with a J.
What? Oh no.
The force is 10, the time 5. So we have an impulse of, what unit would we measure this in?
Minutes.
You'd think so.
It's J, so it's joules, right?
No, it's not. J is the symbol. It's the units of F and T. It's 50
Newtons.
Newton seconds. Not yet known as a Bennett.
I don't know that. So if I put a D on there, it's a good.
I will accept it only because of my vanity.
So Newtons per second. Or Newtons.
Not newtons per second, Newton seconds.
Oh, what?
Newton
Newton seconds, so it's NS?
You don't need it, but it's more commonly used, yeah. It just means multiple. It's kind of like the unit symbol for multiplication. So what is the delta P?
Momentum.
Delta P is the other side of the equation, so delta P is equivalent. It's the same number. It's 50, but because it's momentum, it's not measured in Newton seconds. It's actually meter, or mass, kilogram, velocity, meters per second.
Yeah,
Kilogram meters per second.
Why do we get 50?
Because the impulse is the same as the change in momentum. It's like conservation of energy. If you put in 50 Newton seconds of impulse, you get out 50 kilogram meters per second of change in momentum. Do you?
Yeah, why is it so long as a unit?
Oh yeah, well they really should come up with a guy that they can name that after, right? The kilogram meter per second. So Newton seconds and kilogram meters per second are equivalent. They're equivalent. If you want to call them bents, go right ahead. I won't mark it wrong. Don't do it in university because they'll just mock you and me. What's the final velocity object then? Right? So delta P is equal to m delta V. 50, the mass is 2. So the change in velocity is 50 divided by 2, 25 meters per second. These are pretty easy, right? They're not a lot of math. There's no scientific notation. It's pretty easy. Yeah, usually. The only real way to make it difficult is if the initial velocity wasn't 0, and then you got to do that delta V and VF, V minus VI. Something like that, right? Not too bad, though. All good? This is the last one, isn't it? You guys try that one. Give that one a whirl. Is this a thought equals math question? It sure is. But there's a difference here. You're given two velocities. So what you have to do is you have to find the change in velocity first. So it's going from 20 to 5, final being 5. So how much does the velocity change? Minus 15.
Oh, yeah. What?
It goes from 20 to 5, so it changes by minus 15. F delta T is equal to M delta V for Hannah. Thought equals math for the rest of you. Braking force is 10 newtons. We want to know the amount of time. The mass is 5 times minus 15. Oh, now hang on here. Am I going to end up with negative time? This is going to be, let me think here, 30, 60, minus 75 over 10. Yeah, because why? Because it's a braking force. It's in the opposite direction. You're right. So this should be negative.
If you just put everything as positive, it's not wrong.
No, I probably wouldn't. It's because the change in velocity is in the same direction as the force, right? Now, this is exactly what I was talking about. This is why cars are built to crumple, okay? Because if you increase the time, like if I decrease this time here, if I drop that to 0.75 seconds, how much force do I need to make it all equal? And if this is 0.075, well, then it becomes 1,000 seconds. So if there's some way to increase the amount of time it takes to slow it down, then that decreases the force. Think about if you jump off the table. If you jump, what did you do when you hit the ground? Bend your knees. What does that do? Absorbs, it increases the amount of time it takes to slow down, which reduces the force. If I jumped off the table with my knees locked, I'd probably have a broken leg. Bad idea. Because the force would be great, right? Okay. I think I'm done. Yesterday you got a worksheet that didn't match what I taught you. Now you can do it.
Oh, wow.
of me jumping off the table?
No, we're doing the magnet thing.
Oh, yeah, I'll show you the magnet thing. I will show you because it's like 3 minutes.
So you want to show a video?
Yeah, the video.
I'll find, do some questions.
Like, not a military video, whatever that video was called.
Do some questions from that yesterday's sheet, and then I'll show you.